Hello, welcome to RC Video Reviews. Today we're going to talk about radio frequency technology. You know, it can be very daunting with all these different options out there with video transmitters and radios and crossfires and dragon links and all these different antenna types you can buy. It can be very confusing on what's going on. So this video is intended just to walk you through the basics and give you a foundation so that you can build on and study and decide what's best for your use case. I have to start out with a couple of disclaimers. The main thing I like to point out is that I'm not advocating for anybody to break any rules. That's the bottom line. Anything you see here should not be considered advocacy for violating rules promulgated by the US government, the FCC, the FAA, or any other bureau or agency of the United States government. And the rules are the rules. It's not my intention to get into a discussion on how we enforce those rules or who should enforce them or any of that. That's up to the individual. This is strictly meant to be a technical discussion about hardware and radio theory. Did you know if you're flying radio control with a modern transmitter, you're using microwaves? 2.4 gigahertz is in the microwave spectrum. Microwaves tend to be shorter than regular radio waves because they run in the 1 gigahertz to 300 gigahertz range, whereas normal radio waves run from 3 kilohertz to 1 gigahertz. The main connection you need to make on wavelengths is as a wavelength becomes shorter, its frequency increases. So for the length of time it takes for a radio wave to complete a single cycle, as that wave gets shorter and shorter and shorter, that means the frequency increases and gets higher and higher and higher. You don't have to take my word for it though. Here's a nice little chart put out by NASA. They highlight the entire radio spectrum, and as you can see, I've highlighted the area where we operate in radio control between about 433 megahertz and 5.8 gigahertz. So you might be asking yourself, John, why do I care about this? Let me make the case for UHF. Free space loss for microwaves is about 8.5 decibels larger than UHF at any given distance with everything else being equal. That means the antenna quality, power output, everything else is equal. 2.4 gigahertz microwaves will have an 8.5 dB larger loss than 900 megahertz with everything else being the same. On the UHF side, you do have larger and heavier antennas. Now the case for the super high frequency or microwaves, you've got more bandwidth, less latency, and smaller, lighter antennas. We'll talk about bandwidth and latency next. Hey, if you like the work I do here on RC Video Reviews, please consider joining me on Patreon. For about the price of a cup of coffee, you can help me keep making videos just like this one. If you'd like to help out, there's a link in the description and on your screen. I put this little chart together to give you an idea of the relationship between wavelength and time. As you can see, this wavelength moves back and forth over the x-axis, and the x-axis represents time. So the shorter the wavelength, the more cycles per second a given radio frequency operates. In this example, the diagram shows the radio wave completes 3 full cycles. There's 1, 2, 3 in a span of 1 second. On the left-hand side of the chart, there's a UHF wave represented, and you can see that in the span of 1 second, it completes only 1.25 cycles in the same period of time. So what that means is that if you stipulate the data has to be transmitted at some point in the cycle, we'll just call it when it crosses the x-axis, that means more data is transferred in a given period of time. The time gap between messages is also lower, resulting in lower latency. Now you might ask, hey, what are the new protocols like Ghost and Tracer doing? The reality is that changes to the encoding scheme enables increases in data transferred per cycle, and that's what they're doing. Full datagrams can be conveyed more often with more efficient encoding schemes, and that improves bandwidth and reduces latency. The physics of radio waves can't be changed though, only how the data is transmitted. So what they're doing to their protocol is making changes to their framing or encoding so that they're more efficient and they deliver more bandwidth per cycle. Keep in mind, these techniques do not alter the fundamental rules of propagation. Before I move to the next chart, I want to leave you with this question. Do you think you need more bandwidth? What about latency? Next, I'd like to have a word about polarization. This is one of the most misunderstood topics that I've seen, and I've seen just flat wrong advice about this. Let's talk about linear polarization first. Linearly polarized antennas have more range than circular polarized antennas of equal gain because they don't split their power across multiple RF planes. They only work in one plane. When you have a circular polarized antenna, it's got to split its read power across multiple planes in a corkscrew pattern. On the other hand, though, linear polarized antennas are more prone to multipath interference than a circular polarized antenna, and you should only use them on aircraft with minimal obstacles and minimal attitude changes. CP antennas have less effective range than LP antennas of equal gain because their energy is split across multiple planes. They're really good at multipath rejection, and the reason for that is because when a radio wave hits a surface and reflects back, it's effectively mirrored. So if you have a right-hand circular polarized antenna sending data back to a receiver and that data hits an obstacle, it gets converted to a left-hand polarization and the receiving antenna can reject that out of hand, almost. These types of antennas are best used on aircraft requiring more attitude deviation where RF plane alignment is much more challenging. Keep in mind, for maximum range with a linear polarized antenna, you have to have the receiver and transmitter antenna aligned on the same plane. So these blanket statements out there that say LP antennas should be avoided are by people who don't really understand what they're talking about. And you can ignore them. All right, now let's talk about propagation. Rule number 1, radio waves at lower frequencies propagate further than radio waves at higher frequencies. That's a rule. That's not John making that up, that's just a rule. Rule number 2, antennas reduce the signal strength in some directions and increase signal strength in others. This is called gain. Rule number 3, 900 megahertz will transmit more than twice as far in free space as 2.4 when both radios use the same modulation and output power. Now you can't throw curveballs in here and say, well, if you got a 2.4 gigahertz radio at 1 watt and a 900 megahertz radio at 25 milliwatts, then the 2.4 is going to be better. Yeah, it probably is. It probably is. But everything else is the same, meaning the quality of antennas is the same, the output power is the same, the equipment quality is the same, the antennas are made from the same grade of materials. When everything is held constant, 900 megahertz has less free space loss. That's just a rule. I have 2 antenna radiation patterns on the screen now. The top one is called an isotropic antenna. This is a theoretical antenna. It's meant to be perfect, means there's no gain in any direction. It's perfectly spherical or isotropic. The bottom antenna shows an omnidirectional antenna, and you can see by looking at these 2 images that the omnidirectional antenna gives something up. It's not perfectly radial. It's not a perfect sphere. It's more of a flat torus pattern or a torus ring. Since we don't have perfect isotropic antennas, we wind up changing the radiation pattern, and the distance or difference between the radiation pattern between an isotropic antenna and an omnidirectional or any other antenna is what we call gain. That's what happens when you squeeze or change the radiation pattern by using an antenna that's not perfectly isotropic. As you can see in this example, we lost some of our vertical gain. We no longer can go quite as high as we could with the original antenna, and nor can we go quite as low. But you can see that we can go out on the x-axis further in both directions. This is the gain over the isotropic antenna. All right, next up are RC rules and frequency. FCC Part 15 is a big deal in the US because it permits unlicensed operation for low-power devices. With a Part 15 certification, you don't have to have a license to operate the gear. Think about the radio that you take to fly at the field. If you live in the US and you flip that radio over, you should see a Part 15 certification somewhere on that radio. Part 15 certification means you're not supposed to modify that radio. You're not supposed to change the antenna. You're not supposed to add a booster. The whole point is that the manufacturer said that the equipment operates within the specifications of Part 15, and they certified it as such. When that happens, the FCC allows that device to be sold under a Part 15 certification. Antennas cannot use commonly found replacement parts. That's the nature of seeing a ham license requirement on video transmitters in the 2.4 and 5.8 gigahertz spectrum. Even though those are ISM bands, the antennas are easily replaced, and for that reason, they're generally not certified as Part 15 devices. However, there are provisions for repairing antennas in the guide. Here's a link to the FCC lookup database if you'd like to check out your device. All Part 15 devices have an FCC ID, or you can look them up by the manufacturer. One special note, 2.4 gigahertz is in the ISM band, and there is international harmony on this frequency. It's one of the few that internationally there's agreement. This is one of the reasons why wireless routers can be sold internationally. Here's the big takeaway on this slide. Any intentional RF radiator that's not FCC certified requires a license to operate. More information can be found at the link at the bottom of the slide. All right, let's talk about the most commonly used frequencies in RF. First up is 433 megahertz. That is a UHF frequency. An example of a product that uses this frequency is the Dragon Link control system. Its primary use is control, so that device on the screen is a transmitter, and they also sell receivers that match up on the same frequency. A ham license is required to utilize this product, at least in the US, and in terms of range, very long range, 31 to 124 miles according to the vendor. Next up is 915 or 868 megahertz. 915 is region 2, which is basically the US. 868 is region 1, which is basically not the US. This is a UHF frequency. One example of a product using 915 megahertz is the Crossfire. Its primary use is control. A ham license is not required for this device because it is Part 15 certified and its range is long. The vendor claims 9 to 12 miles of range on this particular device. Next up is the 1.2 to 1.3 gigahertz frequency. This is a microwave channel. One example of a product utilizing this frequency is the ready-made RC video receiver. Its primary use in RC is AV. A ham license is required to operate equipment utilizing this frequency. It has a very long range of 10 plus miles, and I've experienced that firsthand. Next up is the 2.4 gigahertz frequency. This is a microwave frequency, and one example of a product utilizing this particular frequency is a standard radio that you take to the field, like the Radiomaster TX16S. A lot happens in 2.4 gigahertz. Its primary use is control, but it can also be used for AV. A ham license is not required to utilize a Part 15 certified radio. However, you do need a ham license to operate a 2.4 gigahertz video transmitter, especially if it's not Part 15 certified. When it comes to control, the range of 2.4 gigahertz goes up to 2 miles. I've seen that firsthand with an L9R receiver in an airplane. 2.4 can also reach up to 5 miles on AV equipment, and that came from a vendor who I know is very reputable. Finally, we've got the 5.8 gigahertz microwave frequency. An example of products utilizing this frequency are VTXs, specifically the Race Day Quad Mach 3. Its primary use is AV. As far as the ham license goes, you probably need one, although I've heard that there's some Fat Shark devices out there that are Part 15 certified. So if you can find a Part 15 certified device, you don't need a ham license.
Oh, God! No, God, please, no! 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 No!
If you can't find a Part 15 certified device, you are supposed to have a ham license to operate it. Range is very short. However, it goes all the way to 3.6 miles, and I've seen that firsthand. Now, before anyone goes and gets upset, I'm going to show some visual evidence. This is a flight that I did some years ago before we had all kinds of rules about what we could and couldn't do, and you can see on the bottom of the screen, that's 3.6 miles, and that was done on a 5.8 gigahertz VTX, standard store-bought VTX. I did that with a 600 milliwatt generic VTX using IB Crazy Mad Mushroom antennas and SkyZone V2 goggles. I had a little bit of altitude and I had wide open clear space, but if people tell you that 5.8 is only good to a mile, they're just wrong. Okay, next up are hardware recommendations. I thought what would be the point of going through all this if I didn't recommend some hardware at the end. First, I'll throw out the long-range control. I've personally used DragonLink, 433 megahertz. This stuff is not cheap. You can expect to pay around $200 for the transmitter and about $100 a pop per receiver. So not cheap to use this stuff, but the reason I like it is because they've got a proven track record. They're always doing development work on this platform, and they're highly active in the community. Next up, for mid-range control, I really like the TBS Crossfire. 915 megahertz for region 2, 868 megahertz for region 1. I gave it $3 signs on price, which means it's a little bit on the high side at about $70 for a transmitter and about $30 for a receiver. It's not terrible, but it's not exactly cheap either. The reason I like the TBS Crossfire is because, again, they've got a proven track record. There's always some development going on with this product set, and the guys that sell it fly it. Next up, for short range control, you can't beat the Radiomaster TX16S. It supports every protocol. So if you like DSM, it's got it. If you like ACCST, it's got it. If you like FlySky, it's got it. It even supports one of the Futaba protocols. This thing supports everything. Price-wise, I only gave it $2 signs because it's actually very affordable. You can expect to pay about $140 for a base transmitter and up to $220 for a fully loaded with all the bells and whistles like you see here on the slide. Why do I like this platform so much? First off, OpenTX. It's a superior operating system for radios, and that's all there is to it. I also really like that multi-protocol module because I combine with just about anything sold. And RadioMaster also has excellent after-sales support. Next up is long-range video. If you make the choice to fly long-range video, one of your best options is the ready-made RC 900 MHz to 1.3 GHz receiver. I like true RC or VAS directional antennas, and if you really want to maximize your range, you're going to need an antenna tracker. Regarding price, I gave this one $4 signs because you're getting into the money now a little bit. You can expect to spend $35 for the transmitter, about $40 to $50 for the receiver, about $200 for an antenna tracker, commercial or homebrew, and you're going to pay about $75 for a directional antenna or about $25 if you make your own. Why do I like this setup the best? Because it's the lowest frequency and gives you the best range possible. It's readily available, and you've got plenty of antenna options, including the True RC X-Air shown in the picture. Next up is short range video. I really like the Race Day Quads Mach 3 VTX. Again, VAS or True RC antennas. You know, when it comes to antennas, I have a theory on these. Just buy the best ones you can get, because antennas will make or break your experience, assuming everything else works. On the price side, I gave the Mach 3 $2 signs and the VAS and True RC antennas $3 signs. You can expect to pay about $25 for a Mach 3 and $20 to $30 for VAS and True RC antennas. Why did I pick this combo? The Mach 3 supports 1000 milliwatts with smart audio for $25 and it just works. When it comes to the antennas, you just can't beat Video Aerial Systems and True RC for precision design and manufacturing. They just make the top shelf stuff. Next up, I'd like to give you a look at a homebrew antenna tracker that I built some time ago. The tracker is an Eagle Tree Eagle Eyes. Of course, they're out of business now, so you have to choose something else. The directional antenna is a homemade biquad. The Omni antenna is a generic commercial rubber duck that came with the receiver. The receivers I used at the time were Racewood 1.3. Those are no longer available, so go ahead and go with the ready-made RC gear. And then I also used a Fat Shark 5.8 gigahertz relay on the ground, so I didn't have to wire my goggles to the tracker. All right, next up, let's talk about your frequency plan. When it comes to frequencies, you've got a couple considerations you need to make. When it comes to control versus video, look at the picture on the right. That's actually a good thing. Even though I lost the FPV feed, I still had control of the plane. By the way, the antenna in that picture is the one that gave me the 3.6 mile range on a 5.8 gigahertz VTX. The bottom line though is you always want your control range to be greater than your video range, because if your video range is greater than your control range and your failsafe doesn't work, you get to watch your airplane fly away. It's always better to maybe start getting a little hits on your video so you know you're at your limit and it's time to turn around. Next, always have different frequencies for different functions. Do not use 2.4 gigahertz for control and video. That'd be a catastrophic mistake. You'll wind up having one step on the other and you won't be happy with the outcome. Also, you need to spread your antennas out, but you don't have to get mental about it. There's a whole lot of long-range quads that fly and they're not bigger than about 7 inches, so spread them out the best you can, but you don't have to be crazy about it. Be wary of harmonics too. Keep in mind that 2.4 gigahertz is a 2F harmonic of 1.2 gigahertz. So if you use 1.2 gigahertz for your video and 2.4 for your control, that's no good because your second harmonic of 1.2 gigahertz on your video is probably going to step on your control channel. Also realize that 433 megahertz is a 3F harmonic of 1.3 gigahertz, but that one works. The reason I think that works is because by the time you get to that third harmonic, the frequency or the intensity of the signal has died down just a little bit. You can use low pass or other filters to fix harmonic issues, but if you can avoid it, I recommend you do. I'll wrap up by giving you a couple of known working frequency combos. For very long range, consider 433 megahertz for control and 1.2 or 1.3 gigahertz for video. For mid-range, look at 915 megahertz for control and 2.4 gigahertz for video. And for short range, 2.4 gigahertz for control is fine, 5.8 gigahertz for video is fine. Just make sure you don't fall for the 1.2 to 1.3 gigahertz trap. And what I mean by that is 2.4 gigahertz is a 2F harmonic of 1.2. So if you take 1.2 on video and double it, you're at 2.4 gigahertz and you could step on your control surface with that one. So don't fall for it. Stick with 5.8 if you're going to do short range. All right, that wraps up this video on RC RF tech. I hope you liked the video and that you learned something. If you like this kind of content, it's really important for you to hit that subscription button and the notification bell. That's all I've got for today. Take it easy.